Hello, welcome. It's Johannes again here for another episode of Packet Tuesday. And what I picked today is, well, how do you know it's Tuesday? Because you have an accurate time. So I was going to look at an NTP packet. Actually, I have a few NTP packets for you. And I hope you understand the basics of NTP. It's used to synchronize time, and we're dealing with different time servers that we usually differentiate by stratum, where stratum 0 is actually your standard clocks, like GPS or an cesium clock, or these time standard broadcast systems that like NIST and other standard bodies are running. And then of course the NTP protocol is being used to exchange those time signals across the network and help us synchronize time. But well, enough introduction. Let's dive in and look at an NTP packet here. And here I got one. So let's first take the basic packet apart. We are dealing with IPv4 here. We got a basic, a 20 byte IPv4 packet. So that means it ends here. We have 16 bytes per line. So 16, 17, 18, 19, 20. So that's our NTP packet. Nothing really remarkable about this. We do have our datagram size for Charlie. That's and what is this? This is 64 plus 12. Yeah? So we have 76 for our total datagram size. Then we have an IP ID 6 Bravo 82. Then we have our do not fragment flag set here. That's the 4. Of course, no offset. We do have a time to live of 64. This comes from a Unix system, and I collected a packet on the same network segment as that system. So, well, again, nothing too exciting here. And then we got our protocol 11 or 17 in decimal. That means we are dealing with UDP here. UDP is used for NTP exclusively. I don't think there is any way to do sort of TCP. And the big reason is one of the important and critical things with NTP is we need to figure out the latency. How long did this packet take to get to us from that time server? And so consistent latency is important. TCP often doesn't have consistent latency because if you have things like resends, then the packet is being sent later again, and that could mess up your latency. Also, a lot of middleware like routers and such are sometimes buffering TCP. Cable modems are famous for doing that. So that's why we use UDP here for as our protocol. Then we have our checksum, and then we have our source IP 10.5.1, and this is 113, and our destination IP 10.5.3 and 1 Foxtrot, which is 31. Okay, like I said, unremarkable IP header. Next, we have our UDP header. We have our source port, apparently 38,136. We have our destination port, 123. That's the standard port for NTP. And then we have our UDP length. So 38, or that's 16, 32, 48. And the pen is giving up a little bit. Let me try a different pen here. So 48 plus 8. So that gives us 56. And yep, makes perfect sense because we had 20 bytes for the IP header. So 56 bytes less. And then finally, we do have our UDP checksum, and that's where our UDP payload starts. So 2, 3. That's the first part of the NTP payload. One thing I want to point out is, so we had these two different lengths so far. We had 76 for the datagram, we had 56 for the UDP part of the packet. Where does TCP dump pull this 48 from? Well, 56 minus 8 is 48. This is the UDP payload size. TCP dump is actually a little bit inconsistent here. What it displays as length depends on whether it recognizes the application protocol or not and such. So sometimes you see the complete datagram size here. Sometimes you see sort of, IP payload or here UDP payload size here. Have to be a little bit careful when you're looking at that. But anyway, so this is now our NTP payload. And well, let's cheat here a little bit and switch to Wireshark. So same packet here in Wireshark. First, we have a couple of flags. The first two flags are actually kind of interesting. That's the leap indicator. You probably heard of leap seconds, where sometimes a second is being added or removed. And the way this works is that second is always added or removed from the last minute of the last hour of a month. So if this is set here, it tells us whether or not we have to add or remove a second from that last minute. So it gives us kind of a warning that this is going to happen. Here we have no warning, it's 0. And that's kind of good and interesting. I collected this, December. Typically, these leap seconds happen at the end of December or at the end of June. They don't have to happen, but that's what has been done sort of in the past. And yeah, so at the end of 2022, we don't have to worry about leap seconds here. There's also a possibility that both of these flags are set. When both of these flags are set, this means your time is unsynchronized, so basically don't trust any timestamp here. But since this is a client responding, well, we don't really worry about this. Then we have the NTP version number. So 3 bits, so 1, 2, 4. So the 4-bit is set. Let me just pull up the version 3 here. So you have the 1 and 2 bit set. So 3, and this is 4. And then, well, here we are a client requesting the time. So there's client or server. There are a couple other options too that we won't cover here. And before I forget, and before I go any further, let me just clear up some of the notes here. Okay. Next, we have some information about our time status. This is not really important here because, again, this is a client requesting the time, not a server offering a time. So our stratum is unspecified here. It's set to 0. Now you may say, hey, stratum 0, that means it's actually a standard clock, like, sorry, a cesium clock. No. You will never see stratum 0 broadcasting or sending data on the network. Stratum 0 is only the standard clock, like that cesium clock. The lowest stratum that you'll see is stratum 1, which is an NTP server that synchronizes to a stratum 0 clock. When you see stratum 0 in a response from a server, it actually means there's an error message. And then the payload will include the error message. So, okay, but here from a client, it's just invalid. That we basically don't specify a stratum. And then how often are we going to ask for the time? This is always a power of 2. So 2 to the power of 10 is 1,024 seconds. We are not allowed to ask for the time more frequently than every 16 seconds. So values like 1, 2, or 0, 1, 2, and such or 3 are invalid here and should not be used. Of course, the client can just send these requests whenever it feels like, but this is what you're supposed to do. What clients typically do is they request the time more often as they start up, and then once they are more synchronized, then they may back off and ask for the time less frequently. The maximum time between requests, according to the standard, is 36 hours. Clock precision, again, doesn't really mean anything here. Also root delay, root dispersion. This comes in later when we're looking at the reply from the server. And then we have this transmit timestamp. The transmit timestamp is supposed to be the time on the client when it sent the message. And it's echoed back in the response, and then this helps the client figuring out what the round trip time was. I did not travel in the future to get a packet from 2061. Also, the time on this server was actually reasonably in sync. I did not just boot up the server, it already had its time synchronized. So why is it so far off? Well, this is a security feature that was implemented in more recent versions of the NTP daemon. They're really sort of in the Unix world, kind of three different NTP daemons that you typically see. You see NTPD, that's of the traditional NTP daemon. And then you do have Chrony. Chrony is a more modern implementation of NTP. Comes out of Facebook, I believe, and they sort of claim that they can get with Chrony like sort of in the nanosecond range of synchronizing their time. Not really that important for most of us, but most recent Linux distributions, like if you look at a Linux distribution that you installed the last couple of years, you'll find Chrony instead of NTPD by default. And Chrony just sets a random timestamp here because that timestamp is being echoed back. It uses it kind of like a DNS query ID, where it makes sure that the timestamp is the same coming back in order to prevent spoofing of the response. It's not perfect by any means, but a little sort of additional security. And if you think about it, it's better than what DNS does. DNS only has 16 bits. Here we have 64 bits. And actually, while we are here at it, just about the NTP time format. So we have 64 bits. The first 32 bits are the number of seconds. And the remaining 32 bits are then the fractional seconds that we have. 32 bits, of course, allows for 4 billion something seconds, or about 136 years. NTP does not start with the Unix epoch, like the January 1st, 1970. Instead, zero time for NTP is January 1st, 1900. So it's 70 years earlier. There's actually a little bit an interesting thing here that UTC, all the NTP's timestamps are always in UTC. They're not in your local time zone. The operating system then, when it sets the time, has to translate in the local time zone. But UTC actually officially didn't exist until 1973, I believe. But yeah, with NTP, they went back to 1900. If you want to measure sort of larger times, there's also something like an era that you can add to this and sort of extend this to 128-bit timestamps, but that's not transmitted as part of NTP. That's just tracked internally. Remember, we are using NTP to sort of measure time offsets. So we're not going to measure these large absolute time differences with NTP. That's not really what it's meant to do. So anyway, so that's the transmit timestamp. Now let's look at the response here. So again, no leap seconds. Version 4, the mode is now a server. 4, 3 was client. So 4 is server. This particular time server here considers itself stratum 1, a primary reference, because it receives its time via GPS, and that's considered, a standard time source. So that's why we have here stratum 1 for this clock. The polling interval, again, it suggests 1,000 seconds here. And then it tells us a little bit about where it got its time from. So we have here the precision, the delay. This is all 0 because this is a GPS module that's directly connected to this little sort of, it's not a Raspberry Pi, but very similar with respect to the hardware. So for a little time appliance like that. And then this root dispersion really tells us a little bit more about how accurate this time probably is. That's based sort of the accuracy that it detected between different synchronization events here. And this is not that great, I think. It's about 2 milliseconds here. Good enough for me here for my home network, but it's definitely not nanoseconds or microseconds or so as people that are really concerned about times worry about. There are a couple of things, of course, that do require accurate times, like Kerberos, most famously, a lot of authentication stuff, certificate expiration. Certificate expiration are usually not that critical, down to the second or so. Probably the most sensitive about a time are things like large server deployments. That's why Facebook, for example, came up with Chrony and spent a lot of time in coming up with sort of better time sources and such. They developed some open source like hardware to synchronize time better. 5G or in general mobile phone operators, they often need highly accurate timestamps. So for them, something like this would probably be not sufficient. Then where do we get the time from? Now, this is 4 bytes. Notice it's highlighted here, the 4 bytes. If I get my time from another server, it would be the IP address of that server. Now here, I don't get the time from a server, I get it from this GPS module. These GPS modules usually have 2 outputs. There is a signal that gives me basically the GPS time, and then there's this pulse per second signal. That's usually actually considered more accurate, because if you think about it, I don't have to parse a time or something like this, like I need for the GPS time signal. So PPS means I'm using that pulse per second signal that is created by that GPS module, and sort of I'm using the GPS clock as a frequency standard, not necessarily as an absolute. I probably initially start out with setting the time absolute, but then the increments, and I use this pulse per second. Okay, and then we do have a couple timestamps. So the reference timestamp, that's the last time when I actually synchronized my time with the reference. So this is always a little bit back, and it looks like here this happened about half an hour ago. Then the origin timestamp, this is the time that we got from our client. Remember here, this is the 2061 time. Then we have the receive timestamp. That's the time at which we received the request. And then we have the transmit timestamp, which is the time at which we send the reply back. And this is important because that allows us to subtract the time that the time server here spent coming up with the response from the latency. So we can actually distinct between the network latency and the latency on the time server as it processed the packet. So what we would do now, if we try to calculate our time, we have our client, we do have our server. So there's a packet being sent and the response coming back. We have here the time when the packet is being sent. We have the time when the packet is being received. Then we have the time when the reply is being sent and the time when we get our response back. So what we would now look at, we would look at the total latency. So our T3 minus T0. And then from that total latency, we have to subtract the time it took to process the packet. And then we divide that by 2, that would then be our network latency. So this is how long it took for the packet to come back here. So that's sort of roughly the way this is then being calculated to correct for the network latency. But yeah, so this is your NTP packet. Couple interesting things with NTP. So I already told you can do a little bit of operating system fingerprinting here, based on whether or not that transmit timestamp is randomized or not. Also, what NTP servers are being used. Most Unix systems these days use this pool.ntp.org. This is about 4,000, I think. They have now NTP servers that volunteers essentially contribute to that network, and you may use them. They actually work pretty good. I looked at them recently, and their times were really good. But then there are some vendors that also like to use this pool.ntp.org for their devices as a pre-configured NTP server. That has caused some issues in the past where then I think it was D-Link all of a sudden started using like pool.ntp.org, and all these millions and millions of D-Link devices kind of started overwhelming the NTP pool. In order to fix that, the organizers of pool.ntp.org basically reached out to vendors, and now you often see vendors use specific NTP pool time servers like debian.pool.ntp.org. That's what you often see with Debian. I saw, for example, iRobot.pool.ntp.org. That's what Roombas are using, like these robot vacuums. They use that particular time server. So that basically allows vendors to get their own little subdomain here in the pool.ntp.org. Vendors are then also setting up special resources and such that helps alleviate the pressure from the larger NTP pool. And you can see these DNS lookups for these host names, and then basically derive what time server is being used, what operating system is being used. Also, like Apple, Apple has their time.apple.com. Microsoft has similar standard host names that they're using for their time servers. So that helps you sometimes fingerprint operating systems. Just quickly here, NTP version 3. Nothing really too different here, but here we actually have, let me actually go to the server here. Here we have a Stratum 2 server. And so now you get a little bit root delay here, a little bit root dispersion, and the reference ID now is the NTP server this Stratum 2 server is synchronized with. So this would now be the Stratum 1 server that we used here. If there are multiple NTP servers, when you configure an NTP server, even a client, you often configure multiple NTP servers. It does not necessarily just average between these NTP servers. Instead, there is a little bit of more complex algorithm that's happening. So you have like NTP server 1, NTP server 2, NTP server 3, and then there's first sort of selection algorithm that's being used to figure out which one of them is good enough. And there's like things like the dispersion we saw earlier that's being used. There is the latency, because shorter latency usually also means more consistent latency, and a couple other facts are being used to then select one or more NTP servers, and then they're being used then to figure out what is the right time. And actually the standard, let me just go back to the standard, has sort of this neat name for this. Let me see if I can find it. yeah, false tickers are the ones that um, are being rejected. So that these are called false tickers, and true chimers are the ones that are kept in order to actually derive your time. And you basically have this clock filter that basically figures out which clocks are good enough. And have to mention this one quote. I had actually not 100% sure where it came from. I tried to look it up. There are a couple different sources that attribute it to different origins. But if you have one clock, you know what time it is. If you have multiple clocks, you never know what time it is, because you basically don't know what clock to trust. And that's sort of what they're trying to address here, that they remove clocks that are basically not consistent enough, where there's other indicators that they're not trustworthy, where these are your false tickers, and then you're left with the true chimers. That's what you're then using to actually average your time. And the standard here has some sort of reference implementations of how you're supposed to do this, but that's then again up a little bit to the algorithm, and that's where sort of Cronny tried to improve on what like NTPD and some of these older implementations did. But anyway, that's what I have for you today. So thanks again for listening, and hope to see you again next week for another Packet Tuesday. Set your calendars and hope your times are good enough that you'll know when it's at least Tuesday, or well, you can also get them on Wednesday. Thanks.